Good evening, David.
Good morning. Can you hear me?
Yep. Nice and clear.
Go ahead, David.
Hi, Nazri.
Apa tentatifnya? We have 10 more minutes, David, so we will play on the videos and songs and we'll start sharp at 9 local. Thanks for joining.
In 2002, the Ministry approved the establishment of College University Kejuruteraan Utara Malaysia, KUKUM, the 17th public university in Malaysia. In 2007, KUKUM was rebranded as Unimap. Unimap offers programs of study leading to the award of diploma, bachelor's, master's and PhD degrees. Following the restructuring of the university in September 2020, Unimap now has 6 faculties offering more than 40 programs of study. Faculty of Electrical Engineering Technology, Faculty of Electronic Engineering Technology, Faculty of Mechanical Engineering Technology, Faculty of Chemical Engineering Technology, Faculty of Civil Engineering Technology, Faculty of Applied and Human Sciences. Unimap continuously carries out research that brings benefit to all. Nanotechnology research in Unimap looks into faster, easier, and more accurate detection of microbiological diseases. The HPLC kit has high sensitivity that allows early detection of cervical cancer through saliva. A bus monitoring system developed by the Unimap Center of Excellence for Advanced Sensor Technology facilitates efficient monitoring of the movement of university buses for students. Under Unimap's social responsibility programs, an alternative energy source kit known as EPS kit has been developed. Each year, Unimap produces alumni whose presence is felt the world over, in many parts of the world.
Being graduate from Unimap, it really helps me in adapting to the working environment, and it helps me speeding up my learning curve. And I think the best thing about Unimap is they don't just teach you, they prepare you.
The soft skills, problem-solving analysis, as well as a lot of hands-on practical that we practice in lab, it will help the graduates to be more confident when they graduated later on.
Unimap researchers are globally recognized, evident through the acquisition of numerous international grants.
Unimap is my first choice because the programs offered here are focused and they fulfill the expectation of the industry.
Apart from academic and research, which are the university core business, sport, culture and volunteerism are also given due to the attention. It's up to the student to choose which field he or she wants to immerse into.
The success and achievements thus far have placed Unimap on the world stage.
I came to Caltech in 1966 on the faculty, working in relativity. I began thinking in great detail about the future of gravitational wave physics and astronomy. Ray Weiss had been the primary inventor of the laser interferometer gravity wave detector. And his classic paper, written in the early 1970s, just lays it out and says, here's what you have to deal with, here's how you deal with it.
The important thing to do in this field was to do experiments to test the theory. And those are hard experiments because it turns out gravity, relative to all the other forces we know about, is a pipsqueak. It's a nothing.
Between 1980 and 1983, NSF funded Caltech to build a 40-meter prototype. And NSF funded MIT to do a feasibility study. So each of these efforts then, running in parallel, became crucial inputs.
In 1989, we made the proposal to build LIGO. That was a Caltech-MIT joint proposal.
And in 1992, NSF, after very careful review, said, okay, we're going to go forward with this, we're going to fund the project. And this was a bold thing. I mean, NSF took a bold step.
NSF bought in because they had faith in Barry Barish, the most brilliant director of large projects that physics has ever seen.
He immediately saw that some of the things that needed to happen should be happening quickly, like you need to build buildings, you need to build the observatories. And it took years. Hanford got started first, then Livingston. And then, of course, once the facility is constructed, then you have to start putting in the detectors. In 1999, there was a dedication ceremony. The interferometers were working. They weren't working at anywhere near their design sensitivity. There was a lot of work that needed to be done before we were ready to go into the first observing run. Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome. Barry Barish realized that if you're building these big interferometers, you better have a community.
The LIGO scientific collaboration is about 1,000 people. We all want to detect gravitational waves. We all want to start doing gravitational wave astronomy.
We don't have two collaborations saying who detects it first, who detects it better. We work together.
We ran our initial detectors from 2002 to 2010.
We saw nothing. Now, you say, well, that's a terrible defeat. That's not true. The LIGO scientific collaboration was in existence, and they were deeply involved with the data analysis and tracked down everything that we didn't understand about that detector and found out what it was. We had already proposed that in the 1989 proposal, that we were going to do a two-stage thing. We would build the initial detector, and then we would build a follow-on detector with the experience we'd gotten from the initial detector called Advanced LIGO.
We rebuilt our detectors. We've been redesigning them for about 12 years.
So we have more light, better suspensions, and better isolation from the ground, and it's that combination that allowed LIGO to become 10 times more sensitive.
It was Monday morning, September 14th.
I knew that there was something going on because I subscribed to the logs.
This particular log pointed to something that looked like it might actually be a gravitational wave.
What I saw is what's called a time frequency plot, called a chirp. And it was strong. It was unbelievably stronger than anything I expected to be a first detection. It was so strong you could see it by eye. And here was the chirp at Hanford, Washington, and there was the chirp at Livingston, Louisiana. And I thought, my God, this looks like it's it.
It was just perfect. In fact, it was almost too good to be true. When I looked at it, I said, well, somebody must have done something wrong and injected a signal.
Nobody right away believed it. Everybody thought it was a fluke. It was too good. And it took us a while to get to the point where all of us believe it.
It's monumental. It's like Galileo using the telescope for the first time.
When our descendants look back and they ask, what is the legacy of that era for humanity? I think it will be rather similar to us looking back on the era of the Renaissance when we say, well, the legacy was great art, great music. And so I think LIGO and gravitational waves, along with the electromagnetic study of the universe, will be a huge part of our legacy for future generations.
Okay, thank you, Secretariat. Salam Sejahtera and good morning, everyone. We are gathered here for the 9th time, thanks to the monumental effort and initiatives of Dr. Nazri Halif and Dr. Sharifah Narfaiza, as well as the ISICS broadcast control team. Thank you, guys. Hope everyone is having a good day. A special welcome and good evening to our guest of honor and speaker, Professor Dr. David Reitz, as well as good morning, afternoon, and evening to all professors, lecturers, students, and public who have gathered here virtually. We are here to hear about secrets of the universe and how to unbox these secrets by Prof. David. Briefly, before we get to know our guest speaker, let me give a synopsis of what is coming your way. Mainly about LIGO, which is an acronym for Laser Interferometry Gravitational Wave Observatory. It's a huge thing. The title of the talk is Understanding the Universe Through Gravitational Wave Observations, where learning about nature requires humanity to develop new types of instruments that allow us to look at the cosmos in completely new ways. The direct observation of gravitational wave emissions, which are ripples in space-time, is the most recent example of how new types of detectors are producing startling revelations about the nature of the universe. Through these observations, we are beginning to answer fundamental and long-standing questions about the nature of black holes, neutron stars, gravity, and the origins of the heaviest elements found in nature. Enabling these discoveries are devices capable of measuring exquisitely small distances produced by gravitational waves as they pass through the Earth. In this presentation, Dr. David will give an overview of gravitational wave astrophysics, highlight some of the most exciting discoveries made to date, and discuss how we detect gravitational waves with LIGO, using LIGO, using really big interferometers capable of sensing distances much smaller than atoms and even protons and neutrons. And carrying on about our distinguished speaker, Professor David Reitz holds joint positions as the Executive Director at the LIGO Laboratory and Research Professor of Physics at the California Institute of Technology, Caltech. He obtained a PhD in physics from the University of Texas, Austin in 1990 and spent more than 20 years as a professor of physics at the University of Florida before joining the faculty at Caltech. His research focuses on the development of ultra-sensitive gravitational wave detectors and gravitational wave astronomy. Reitz was elected a Fellow of the American Physical Society in 2006, Optica in 2015, and the American Association of the Advancement of Science in 2019. He was awarded the National Academy of Sciences Award for Scientific Discovery in 2017 for his leadership role in LIGO. He is a member and former spokesperson of the LIGO scientific collaboration that received numerous awards for the first direct detection of gravitational waves in 2015, including the Special Breakthrough Prize in Fundamental Physics in 2016, the Gruber Prize for Cosmology in 2016, the American Astronomy Society Bruno Rossi Prize 2017, the Royal Astronomical Society Group Achievement Award A 2017, the Princess Asturias Award for Technical and Scientific Achievement 2017, and the Einstein Medal from the Einstein Society of Switzerland 2017. He serves on numerous advisory committees for the international physics and astronomy communities. And with that, I pass the floor to Prof. David.
Thank you very much, Prabha. That was a very, very nice introduction, maybe the nicest I've ever had. I'm delighted to be with you. I'm really pleased that I was invited to be able to speak with you and tell you about some of the exciting things that are happening in gravitational wave astrophysics. And as I go through the presentation, I'm happy to take questions. If you have a question, please raise your hand. I'll try and monitor the window so that I can see what you're doing, so see your question. Let me try and share my screen. That's always the first thing to do. Okay. And now let me go into full screen. There we go. And hopefully people can see my screen. So
yes, it's clear.
Great. So as Prabha said, I want to talk to you a little bit about some of the major scientific breakthroughs that have been accomplished in the past 7 years using these exquisitely sensitive instruments called gravitational wave detectors. But I thought I would start by thinking a little bit about why it is that we study the universe and what we do. Humankind's place in the cosmos is something that we have always aspired to understand more. And one of the ways that we do that, at least one of the ways, scientifically that we do that, is to look to the stars. And for me, this really is inspirational. I actually started my scientific career wanting to be an astronomer because I was just mesmerized by by all of the stars in the heavens, and that you could build these wonderful telescopes to see them. And it's really, as I'll get into it a little bit more, this sort of desire to know more, love of knowledge, that I think is very important in advancing humankind's understanding of the universe and what our role in the universe is. So one of the things that we get when we look at the universe is that there are these objects out there. They're called stars. The closest one of the stars to us is our sun, which we rely on for really for life. And using telescopes, people like Johannes Kepler, Galileo were able to determine that objects are bound together through a force, through an invisible force that we call gravity. And this force of gravity, something you're very familiar with. You have to, every time you climb a stair or climb a mountain, you fight gravity. But it turns out that gravity is really a very subtle and complex force, even though it's something that we live with every day. And it was Albert Einstein who had a number of really important insights about the nature of matter, the nature of energy, the nature of space, the nature of time, that ultimately came up with a theory in 1915. So this is over 100 years ago. That gravity is actually a manifestation of the interaction of matter and energy with space and time. And the matter and energy in this case are the sun and the earth. And the space and time is basically the geometry. It's represented by that green grid that you see. And unlike the geometry that we're all familiar with, that we learn, maybe perhaps you learned it in high school or in university, the geometry is not all right angles and flat surfaces. It's actually quite more complicated, and it can bend. So in Einstein's view of gravity, space and time actually are warped by the presence of matter. And of course, the sun is a very massive object, so it warps space-time a bit more than the sun. So you see than the Earth. So you see the dimple over there. And critically, this theory predicts that the reason the Earth is going around the sun is not that there's some magical force that attracts these two objects, which is what Isaac Newton came up with, but that the Earth is following its natural path. Einstein would call it a geodesic, but we would call it basically a line, the most natural straight line. In this case, that's not straight, it's actually curved. So the attraction between two objects is really due to this interaction with the underlying geometry of space-time itself. And John Wheeler, who was a famous astrophysicist and physicist of the 20th century, had a nice way of summarizing this. He said, space tells matter how to move, and matter tells space how to curve. All right. Well, if you look at that the sun, you see that the warping of space, the bending of space is much more significant than the Earth, and that's because the sun is a much more massive object. Well, it turns out that general relativity predicts something else. It predicts something called a black hole, and theoretically, this was realized maybe even almost 100 years ago in the 1920s. What a black hole is, a very simple object, but it's also very complex at the same time. A black hole is basically an object that is so massive that it basically collapses onto itself, and all of the matter gets confined into a very, very tight region of space that ultimately has infinite curvatures. In other words, that well goes down to a point. And these are very exotic objects. It wasn't until maybe the 1950s or maybe even 60s that we truly had evidence that these objects exist in nature. They were a prediction of general relativity, but we didn't necessarily know that they predicted in nature. And recently, actually more recently than some of the LIGO discoveries, there's a wonderful experiment. This is actually done by a group of radio telescopes where they're able to image, it's really a shadow of the black hole at the center of our Milky Way galaxy. So this is an object that's called Sagittarius A. Sagittarius is the constellation that it is in a star that it is in the sky. And the object that you're looking at is basically the shadow that's cast by radio waves that are collected by a network of telescopes and then reconstructed into this wonderful image. And the character of the image, the fact that it's lighter down below and less light, more red above, actually tells you something about the nature of the black hole itself, how it's moving, how it's spinning. And I should point out that one of the team members that imaged the first black hole is Dr. Kevin Koay, who is actually from Malaysia. He got his engineering degrees in Malaysia. So now let me turn to what I really want to talk about here. I just wanted to set the stage with those earlier slides. So what are gravitational waves? Well, they turn out to be a natural prediction of another natural prediction of Einstein's theory of general relativity. Any object that accelerates, so for example, if I have an object and I drop it on the ground, as it's accelerating downward, it feels the force of gravity. It's actually radiating tiny, tiny amounts of energy. And that radiation is much like the radiation that you would have if you have charges moving around. If you have, moving electrical charges generate light. Well, this is the same kind of thing, only it turns out to be a very, very tiny amplitude of a gravitational wave. So if I were to sort of drop maybe a rock in water, all right, the surface of the pond, we can think about that as the surface of space-time, would generate some ripples. Well, in order to really see these gravitational waves, in order to observe them, you really have to have massive objects such as these black holes. Now, the black hole that I showed you on the previous slide, the one at the center of the universe, is supermassive, and I mean that literally. It's called a supermassive black hole. It has about slightly more than 4 million times the mass of the sun in a very, very compact object. In this case, I'm going to be talking about throughout this talk black holes that are not nearly that massive, but are much more massive than the sun. So maybe 30 solar masses, 30 to 50 solar masses, some a little lighter, some a little heavier. Einstein, when he predicted that these kinds of phenomena, gravitational waves, exist, he actually had a very complicated relationship with them. The history of Einstein and gravitational waves is interesting in its own right. But the one thing that he got right, that he understood, was that in the 20th century, when the theory was developed, And when the theory was expanded and when experiments were trying to be done to prove that general relativity exists, mostly through astronomical observations, but not exclusively, it would be nearly impossible to build a device that could measure these kinds of gravitational waves. And so this cartoon that I'm going to show you is really just to sort of make the connection with ripples in space-time. And in this case, those two black dots there are two black holes, and they're orbiting around one another. And as they orbit around, they're actually speeding up. Their orbit is decaying. In other words, they're getting closer and closer together, and then they eventually merge and produce a burst of gravitational waves. And you can think of that green grid there as the ripples in space-time, in the geometry of space-time itself. So that's really conceptually what to get you calibrated on what gravitational waves are. But if you want to measure them, you truly have to understand physically what they are. And gravitational waves are actually not displacements per se. In other words, they're not amplitudes that you can measure in meters, but they're actually, or micrometers or nanometers, but they're actually strains. And a strain is a particular physical quantity. Engineers know it very well. Material scientists know it very well. It's basically a change in length, and that's that quantity delta L. I don't use many equations in this presentation. There may be a few. I think this is one of them. Delta L over L. So the delta L is the change in length, and the L is the displacement over which you measure it. How far do you measure it? And so if a gravitational wave were if generated by something, by these maybe two colliding black holes or maybe colliding neutron stars, and they were coming out of the screen, if they were coming towards you, what would happen is space would stretch at one point, and then it would compress along the horizontal direction, and it would do the same thing but with the opposite sign in the vertical direction. So while it's stretching in the x direction, it's compressing in the y direction, right? And the fact that it's a strain, and by the way, this is the physical quantity space. What we're actually doing here is compressing and squeezing space-time itself. Basically, distances are getting shorter or greater by very tiny amounts. And I should point out that strains are something that are very common if you're applying forces to bars. The bars compress, but compressed by very tiny amounts. So this is not an unknown quantity. So this suggests that if you look at that equation, that delta L, the displacement or the change in length over the length, that's the L. The backslash is a dividing sign there. It suggests a way to measure them. If you're close to this origin where the two black lines cross, all right, and you try and make a measurement near the origin, the displacement isn't very big because the baseline, the distance from the origin you're measuring, is very small. But if you go far away from the origin, all right, you get a much bigger displacement. The strain is the same. In both those cases, the strain is identical, but the displacement is much larger. So this suggests that you want to make a measuring device that's very large. And you'll see that as we go forward. So another thing to say about gravitational waves, just sort of emphasizing quantitatively what I said earlier, is that amplitude, which is the strain now, that's the thing we're trying to measure, is very tiny. It's 10 to the minus 21. And if you're not familiar with scientific notation, that's 0 point with 20 zeros after it and then a 1. So this is a really incredibly tiny number. And as an experimentalist, as somebody who wants to measure these kinds of phenomena, you have to ask yourself, how could you possibly do that? In fact, the first time that I became aware of this experiment, I was actually in graduate school in the 1980s, and I thought to myself, the people that are trying to do this are crazy. There's no way you can ever measure something that small. However, the more I learned about it, the more I convinced myself that it was actually possible to do it. So they're difficult to detect. Albert Einstein himself thought they could never be detected. So why would you do experiments to search for them? And the answer comes back to the fact that we're curious. The fact that we believe these things exist makes us want to try and build devices that find them. That's great. But there's a much more important reason, and that comes back to this issue of curiosity about the universe and how the universe is composed. Everything we've learned about our cosmos up until now has really come from, generally speaking, three broad types of instruments. Well, two broad types of instruments, either telescopes or subatomic particle colliders. So the telescopes, come in many flavors. There's optical telescopes. That's a picture of the Keck telescope on Mauna Kea in Hawaii. There's neutrino detectors that collect neutrinos from cosmic sources such as supernova. There's radio telescopes, and then there's the opposite side of that. So the telescopes look for things that are very big and very far. Particle accelerators look for objects, or try and basically collide subatomic particles at very highly relativistic speeds. And both, of course, have revealed a tremendous amount about the underlying physical nature of the world we live in. However, gravitational waves are different, and they're really fundamentally different in many ways. So the first thing about gravitational waves is that in order to detect them, as I said, their amplitudes are very tiny. You need really, really massive objects that possess masses many times the mass of the sun. In some cases, there are other sources that maybe are a little bit harder to detect, maybe a little bit less massive. But in order to see those events, you actually have to be looking at what I would call cataclysmic events, the most violent astrophysical events in the universe, when two black holes collide or when two neutron stars collide. In fact, the Big Bang, the beginning of the universe, produced gravitational waves. Very difficult to detect, but we are searching for them. So they tell us new things that we can't see with these other types of instruments. They travel unimpeded through matter. Right now, everybody on the Earth is being bathed by gravitational waves that are generated from the moon orbiting around the Earth, generated from the Earth orbiting around the sun, generated from astrophysical sources that LIGO detects. Of course, you don't notice it because they go right through you. This is a consequence of the fact that gravity is a very, very weak force relative to other forces. I think in the video you saw Ray Weiss say it's a pipsqueak, and that's a very good way of thinking about it. Gravitational waves do not intercouple to matter. They travel at the speed of light. This is a direct prediction of Einstein's theory of general relativity, and it took LIGO and Virgo, the two detectors that we use, a very unique event to be able to prove that. So they carry different information. They carry information about relativistic objects moving and colliding towards each other, which is different from what else we see. So here's a great example of a gravitational wave generator. This is a supernova. And after the supernova happens, of course, this is a simulation. What's left behind in this case is a neutron star. The map that you see below you, or that you see, that's San Francisco Bay, and that little peninsula on the right is San Francisco. So these are very compact objects. In diameter, they're roughly about 25 kilometers, maybe a little bit more, maybe a little bit less. All right, and they're produced when massive stars, more massive than the sun, explode. Now, that's one sort of object that we're going to be thinking about here. The other object itself is the black holes. I've already told you, if the stars are massive enough, the star will actually collapse after the supernova. The matter that's left behind is imploding upon itself, and there's no force. Even though gravity is a weak force, it's ultimately it's going to win if you have a lot of mass there, and there's no force to restrain the object from collapsing, and eventually it collapses into what we would call a singularity. And that block that we see, the event horizon, is basically the point at which in space-time where no light can get out. So if you fall into a black hole, you won't get out. In fact, you'll actually be sort of spaghettified or shredded as you go in. So it's not something you don't want to get too near a black hole. So these are the kinds of objects that we're going to be dealing with, and they're really quite, unlike stars, they're much harder to detect. So there are many kinds of questions that we can ask that are sort of fundamental questions based on what we know now that gravitational waves might answer. And this is really why I got involved in this experiment, why many others got involved in this experiment, because it actually probes really the frontiers of our knowledge. So one question is, where does general relativity break down? In other words, it's the working theory of gravity. It has been around for 100 years. It has stood the test of time. However, we also know another very fundamental theory is that of quantum mechanics, which is the theory of the very, the microscopic, the nanoscopic, it's atoms and things like that. And those two theories have not been able to be brought together, although many people have tried over the last really 100 years since quantum mechanics and general relativity have been around. So at some point, there's a belief that general relativity should break down and lead to a better theory that incorporates quantum mechanics, but so far it hasn't. No test that general relativity has been given has it failed. Why might gravitational waves be that test? Because we're probing gravity in a very unique arena, in a very unique place, where it's very dynamical. Space is moving very, very fast dynamically, and it's also a very high regions of curvature. So we're in a place where dynamical gravity is very, very strong. All right. So I think it's very, whether we'll actually see general relativity breaking down with gravitational waves is a long shot, but we're going to keep looking for it. Are black holes fundamental? In other words, do they truly behave the way general relativity predicts they behave, which is they basically consist of two quantities that you can measure, their mass, and the mass is proportional to the curvature, and their angular momentum, the spin. In other words, these black holes are born sort of like tops that are spinning around in space, and astrophysical black holes could be general relativistic black holes, or they could be more complicated. So that's one of the things we look at. How does matter behave under extreme conditions in nature? This is a really fascinating question that I'll get to more later in the presentation. But if you have objects such as these neutron stars, which are, as I told you, are very dense objects, they're primarily made up of neutrons, as their name suggests, and you can think of them as nuclei. Like you see nuclei, you have nuclei at the center of atoms, but in this case, the nuclei is giant. It's 25 kilometers, and the mass, it has about one and a half, a little bit less times the mass, or a little bit more times the mass of the sun. And there's a range of masses, and so you can think of these as giant atomic nuclei that when they collide with one another, if they happen to be formed in a binary system, they will eventually collide with one another and create conditions that are so extreme that you can start to understand more about nuclear physics in a way that you couldn't using Earth experiments that you do on Earth using particle colliders, for example. Related to that is because these neutrons, stars are so compact, when they collide, they actually allow the neutrons to be released, but in a very dense environment. And there's a process called nucleosynthesis, which actually forms the nuclei of the elements. And that's a topic, again, I'll talk about later. How do massive stars explode? the movie I showed you was a nice artist's conception of how it explodes, but in fact, we don't know everything about that process. The astrophysicists who study stellar explosions, there's still a missing piece of the puzzle as to why stars, once they collapse, then there's a bounce, why the shock continues to move out of the central core of the star and blow off all of that matter that you see. Those are nebulae that are formed in the aftermaths of stellar explosions. That piece of the puzzle isn't there, and it might be that gravitational waves, because it looks at the various cores of these stars, could be able to answer that question. Can we find clues to dark energy and dark matter? These are two. Dark matter has been known for again almost 100 years. We have no idea what it is. There are lots of theories about what it is. There have been lots of experiments to try and look for it. Turns out the universe is, in terms of matter itself, is mostly made up of dark matter. Dark matter is roughly 85% of the matter that's in the universe. It's not protons, electrons, or neutrons. It's not baryons. It's fundamentally different. It doesn't radiate effectively. It doesn't couple effectively to anything. So what is it? And perhaps with observations of gravitational waves, we could get hints into the nature of dark matter. Dark energy is even more exotic. This is something that wasn't even known 30 years ago. Turns out the universe is not only expanding, it's accelerating. And it's, in other words, stars are moving further and further apart, and they're moving more rapidly as time goes on, further and further apart, because of some really unknown quantity called dark energy, which is, somehow pushing objects in the universe further and further out. No one really knows what it is. Can we, using our gravitational wave detectors, be able to see that? That could be a really exciting discovery if we could. And finally, when you build new instruments, you don't know what's out there. We might see something that really surprises us. Certainly, it was true when the first telescope was developed, that you could look at stars, and soon after, you realized that there were objects called planets, and those planets had moon. Very close to where I am right now is the Mount Wilson Hooker telescope, which was built in the early 1900s, and it's the place where the first measurements of the expansion of the universe took place. And at that time, it wasn't even clear what the nature of galaxies were. So these new instruments, telescopes, same thing is true for particle colliders. They discover things that we couldn't, as human beings, possibly anticipate, because we don't know everything ahead of time. We have theories, we have measurements and observations, but we don't know it all. And we hope, one of the other reasons that I think people get into science is to discover things that no one else thought about. So now one slide of history. The first gravitational wave detector was built in the early 1960s by the gentleman on the left. His name is Joseph Weber. And he built a big, massive aluminum bar. This bar weighs many tons. And he was trying to detect gravitational waves as they pass through the bar. If the gravitational waves had a frequency that was resonant with the frequency of the bar, if you ping the bar, it rings at about 700 hertz, which is in the audio band. You might be able to detect them. And those little squares that you see are basically transducers that are designed to pick up the vibrations that are created as a gravitational wave excites the bar detector. And in fact, this whole thing was cooled down. It was in a big vacuum tank, very, very complicated apparatus for the time. But you'll recall that I told you that in order to see gravitational waves, you really need big detectors. In other words, you need baselines that are very large. And this is not a very large object. It's about a human-sized object. In fact, we have one at one of our observatories. We were able to get one of the two original detectors. So unfortunately, Weber never detected gravitational waves, and it's not at all surprising because his detector just wasn't sensitive enough to do that. So what do? Well, Ray Weiss had the very good idea, actually, along with some scientists in Russia, to use something called interferometry to measure a gravitational wave. And I'm going to show a video here of what this interferometer, what an interferometer actually is. And I'll sort of set it up by saying that the cylinder, the white cylinder, that's a laser. It produces very, very coherent light, which effectively means that the wavelengths are very well defined relative to each other for long periods of time. The little line in the center is something called a beam splitter. It splits the light into two equal portions. One portion travels through the beam splitter and goes to the upper left. The other portion is going to get turned 90 degrees and go to the black circle at the upper left. Those are mirrors, in fact. And then the square is the receiver. It basically picks up the signal. So let me run the video here. So you're going to see two wavelengths come out. They're the same wavelength. They're just color coded so you can see which one goes down the horizontal arm, which one goes down the vertical arm, the other arm. They come back. And depending on the difference between the lengths of those two arms, the light that comes back destructively interferes with one another, which means one of the waves cancels out the other, unless there's a gravitational wave. So this gravitational wave changes the length of one arm relative to the other, and it breaks the destructive interference, and so now you can see a signal. So what effectively is going on here is that as a gravitational wave passes, it's changing the length between the beam splitter, which is still in the picture, in the mirror, which you can see in the one arm, the horizontal arm, relative to the other arm, which you can't see now in this zoom. And that's happening dynamically. I mean, it's happening in real time. The lengths are changing as the gravitational wave passes. And it produces a signal which you can record. In this case, it looks like a screen. In our case, it's basically a photo detector. It's like you might find, in your in simple optical devices like DVD readers and things like that. All right, so that's the principle. And the beautiful thing about the interferometer is that it's actually a broadband device. In other words, its frequency response is not for a particular wavelength, but it's actually over a broad range of wavelengths. So now let's get to the big. All right, so in our case, in order to detect gravitational waves, the idea is that you have to make interferometers with the arms that are really, really long. And in our case, they're 4 kilometers long. So the laser in the picture on the right, the laser is in that building that's in the lower right-hand corner there. The mirrors, the end mirrors, you can't even see one of them, but you can see the building that houses the other one. And the light actually has to travel 4 kilometers. In fact, it travels a lot longer than that. That's one of the tricks we play. All right, so I said that gravitational waves were displacements, over length, so delta L over L. So the L in this case, the length, the baseline over which we're measuring the gravitational waves is 4 kilometers. What does that mean? The sensitivity has to be. And ultimately, if you're building these devices, it's the displacement sensitivity that is the thing you have to focus on once you know what the length is. And the answer is that this requires measuring displacements to less than 10 to the minus 18 meters, or about, again, 0.17 zeros and a 1. How small is that number? It's really small. So I'm going to show a video that was produced for us when we made our first announcement of gravitational waves. And this is an artist's conception of a hydrogen atom. All right, so what you see in the center of that blue fuzz is the nucleus, which we're going to zoom in on later. The yellow cloud, if you will, is the electron going around the nucleus. And what I want to do is sort of give you some perspective to say, okay, we're going to zoom in on this hydrogen atom and try and determine how small 10 to the minus 18 meters is. Here we go. All right, so we're going to start zooming in. All right, and these are factors of 10. These grids that you're seeing are factors of 10. Now we'll get to the nucleus, and we're still zooming in. We zoom in about 1,000 times more. And the gravitational wave would stretch the proton, the nucleus in this case is just one proton, by two tenths basically, or 2/1000ths the diameter of a nucleus. So these are really tiny displacements. I could put another way of putting a perspective on that is to say, if we wanted to measure the distance from the center of the Earth to the center of the sun in our solar system, with the precision that we're going to be measuring gravitational waves, we would have to make that measurement to precision of the width of a hydrogen atom, about 1 angstrom. All right. So again, these numbers, it's really hard to describe how small these numbers are, but these are the ways we try and do it. So we have 2 observatories, and there are lots of good reasons for having 2 observatories in the United States. One of our observatories is in the state of Washington in the northwest corner. The other one is in the state of Louisiana, sort of in the southeastern part of the United States. You can see the observatory buildings look very similar to one another because they're built to be identical. The environs, the places where they are quite different because the state of Washington is quite different from the state of Louisiana. And here I should point out that our observatories actually are open to the public. You can visit if you ever travel to the United States of America and are near Baton Rouge, Louisiana, or New Orleans, Louisiana. You can visit our Livingston Observatory. And if you're in the Seattle area, it's a bit of a drive, but you can visit the Hanford Observatory, and they're really very interesting observatories if you happen to be able to do that. So, okay. However, we should point out that, and this is a really important point that I haven't talked about, but I want to emphasize it, that to do experiments of this complexity, to build observatories of this precision, you need large teams. So the team that I work with in the LIGO laboratory is almost 200 people, and they're made up of scientists. Some of the scientists are laser scientists, some are quantum optics scientists, some are material scientists, some are computer scientists. We have a lot of people that do data analysis that come out of they're theorists, they come out of the theory community. We also have a lot of engineers, mechanical engineers, electronics engineers, optical engineers. So to construct and operate these devices, these observatories, it takes a team, but there's even a much larger team that's needed to actually analyze the data and actually help operate the detectors. And so there's the LIGO scientific collaboration, which I'm a member of, is about now 1,500 people. Again, many scientists and engineers. And we work with colleagues from Europe and also from Japan, who have also built gravitational wave detectors. There's a picture of a couple of them. You see the Virgo Observatory near Pisa, Italy, and the Kagra Observatory is a Japanese observatory. It's underground. It's near Toyama, Japan. There's also a couple, the Geo Observatory in Germany, and we're actually working to try and build a third LIGO detector in India. We hope We hope that it will come in the 2030s or earlier. It's been delayed quite a bit, but we're hoping to get it built. And you might ask yourself, well, if you have one gravitational wave detector, why do you need 2 or 3 or 4 or 5 or 6? And the answer has to do with, well, there's many ways to answer that question. The answer has to do with data verification. You want to see these instruments are so sensitive that anything can disturb them, but it also has to do with the way we actually detect where the gravitational wave is coming from. And I'll say more about that in a moment.
Dave, before you carry on,
right?
Can I just ask why Japan has gone underground? Is there any difference? Yes.
So it turns out the surface of the Earth is a very noisy place in terms of seismic vibrations. If I live in California, we know what earthquakes are, but even when there's not an earthquake, the Earth is actually moving at a peak amplitude of about 1 micron or so relative to its ambient at a frequency of about 1 hertz, maybe a little less. And so, 1 micron is 10 to the minus 6 meters. We're trying to detect things that are 10 to the minus 18 meters. So we have to figure out how to build systems that will basically suppress that motion by a factor of 1 trillion. So that's the hard thing about doing gravitational wave detection on Earth. Turns out if you go underground, in the case of Kagra, there are a few hundred meters underground, depending on where you are, because it's in a mountain, anywhere from a few hundred meters underground to maybe even almost a kilometer underground. The surface waves that actually cause those vibrations on the surface of the Earth are very much attenuated. So the motions that are generated from just ambient seismic conditions are down by a factor of 100 or even 1,000 relative to Earth. So it makes it much easier to measure, control, and suppress seismic vibrations. That's really the reason.
Okay.
Okay. Yeah, I'll pause here. And if there are any other questions, please ask. The next, I'm waiting for a question. On the next topic I'm going to talk about is a little bit more complex, and it's probably the most complex part of the presentation, because I'm actually going to try and see if I can explain the real challenge of building these gravitational wave detectors. And Prabha's question comes really right at this topic, so it's a very good segue into this. So the problem, as I said it in answer to the question, the surface of the Earth is a very noisy place. And there are 3 types of noises that we worry about. And by noise, I mean something that perturbs the the components of the interferometer. And the first are noises that shake the mirrors. So if you put a mirror on the ground, as I already told you, the ground is moving. So you have to understand how much noise is there and how to suppress it. The second source of noise that can actually shake the mirror, and this one is very subtle and perhaps counterintuitive, is what we physicists call quantum radiation pressure. So this is noise that comes directly from the fact that light, you can think about it as a wave, but you can also think about it as a photon. Light is quantized. In other words, it comes in discrete packets of energy called photons. And those photons not only have energy, the sun provides us a lot of energy, but they also have momentum. So as the photons hit the mirror, they can actually move the mirror by tiny, 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 tiny amounts. And you might say to yourself, well, how much momentum can a photon carry? How much force can it impart? And the answer is, well, we have a lot of photons. We're not just one photon. We have, the photon flux is 10 to the, I forget the exact number, but it's, billions times billions per second hitting the mirror, and those photons don't arrive at the same time. So they impart basically a random force on the mirror that can actually statically push the mirror by microns, all right, which again is much bigger than we're used to. So we've got to worry about that. And then there's the third source of noise that comes into this shake the mirror category, in other words, displace the mirror, is what we term thermal noise. And this one, again, is also a little bit subtle to understand, but it comes from the fact that all of our detectors are operating at room temperature. So they're operating at basically 273 Kelvin, 25 to 30 degrees centigrade. And statistical mechanics, the branch of physics that thinks about statistically how energy is deposited in objects, tells us that each atom and each molecule has a tiny amount of energy. It's proportional to the temperature that you have, and if the temperature is finite, then there's energy. And those molecules are macroscopically moving around with the mirrors. And I'll show you an example of that. Maybe let's see if I can. Yeah, I'll show you an example of that here.
Dave, can we break that? There's a question by a certain Mr. Collins. Mr. Collins,
Okay.
if you'd like to ask a question, please switch on your camera.
Hello.
Hello. Good morning, Mr. Dr. Professor David. Okay, I'm Collins Edet. I'm a student here in Malaysia. Talking about the LIGO detector, I know it works with the principle of cavity optomechanics. That's the fabric parrot cavity.
Correct.
Yeah, so you were talking about the sensitivity and some of the limitations you're mentioning. Are there currently proposals, or I am actually suggesting you could look in the direction of cavity magnomechanics because of the tunability and the sensitivity? I don't know, it's a suggestion, and I think maybe the center could look into that direction because magnoms are currently being considered actually.
It's a suggestion. It is a good one. One of my colleagues, who is a professor at MIT, Nergis Mavala, has actually thought a lot about this question of cavity optomechanics, and in particular, the interactions of light with these macroscopic objects. So if you think about cavity optomechanics, you think about objects that are, grams, very, very tiny. And that's because if you want, cavity optomechanics naturally leads to sort of you can start talking about quantum ground states and things like that, and the interaction of the laser field with the mirrors. You can actually, pull energy out of a certain mode of the mirror using this coupled cavity optomechanics, and a number of experiments have been done on those in those arenas. It turns out it's a bit difficult for us because our mirrors, that mirror that I'm showing you in the picture is 40 kilograms, so it's decidedly not a quantum mechanical object. It's very much a macroscopic object. But we've actually done some preliminary experiments. I haven't done these. My colleague and her students have done these. Some experiments where you can actually show that you can cool the mirror. In other words, one particular mode of the mirror, thermal mode of the mirror, can be the temperature can be reduced till a point where you get just a few quanta of phonons, a few quantas of energy in that mirror. So I think what you're proposing is actually a very good idea. And in fact, I think there's a number of people that are thinking in that direction. So I congratulate you for thinking about it.
Okay.
Great.
Thank you, Prof. Thank you.
Great. Okay. All right, so this is, let me come back to this idea of temperature, which I was talking about. So this is one of our mirrors. This mirror, like I said, is 40 kilograms. It's a really great mirror. In other words, the surface of the mirror is polished exquisitely well. The coating, you can see that sort of pink tint is actually the coating on the mirror. And that coating we worked very hard to get some of the best optical coatings in the world. There's a lot of technology and a lot of interaction with companies that do these kinds of things. In this case, this company is based in Europe. But because these objects are at finite temperatures, they actually, oops, let me get back to the surface is actually moving. All right, and the surface is moving in a very predictable way. We know how it moves because we know what the normal modes of mechanical modes are. But it turns out that the coating actually causes us real problems because the atoms, and in this case molecules, this is fused silica and something called tantalum pentoxide, are moving, and that actually leads to motion on the surface of the mirror that interferes with our measurement. And so the picture that you see, the lines coming to the right are laser wavefronts. The lines that are bouncing off the mirror are distorted because of this motion. And it turns out, again, this is a very tiny effect, 10 to the minus 20th meters, but we're trying to measure things that are almost 10 to the minus 20 meters. So it's a problem that we have to understand. And there are many good ideas in material science that we're borrowing and working with material scientists to try and build better coatings. Let me come back to this slide again, and probably, please, if there's more questions, please let me know. I didn't see the question before. So there are also there's a second class of noise. So the first class that I talked about, and you can see the pictures of how the noise actually breaks down and affects the interferometer. The second class of noise is noise that changes the arrival time of the light. So fundamentally what we're measuring is the displacement, is basically the change in light travel time between the beam splitter and these two arms of the interferometer. And that tells us what the gravitational wave signal is. So there are two aspects, there are two things that can change that. First is the arrival time of the light. I'm sorry, something called the quantum phase noise. It turns out that a fundamental principle of quantum mechanics is that if you have a bunch of photons that are produced in a laser, they're not perfectly correlated. There's always one photon comes a little bit later, a little bit less. Another way of saying that in the wave picture is that the phase of the light at some points is a little bit different from other points. And that randomness in phase actually leads to basically a signal at the output of the interferometer once the beams are recombined that looks very much like a gravitational wave signal. It's very random. All right, so you have to do things. It turns out the way to handle that, there are two ways to handle that power. One is to turn up the laser power. The other is to use something called squeezing, which I'm not going to spend any time on. The other problem is residual gas noise. So if you send light through the atmosphere, turns out the atmosphere slows the light down because the light interacts with the molecules, the oxygen, the nitrogen, CO2, and depending on the color of the light, the wavelength of the laser, that interaction can be substantial. And so we basically have to get rid of all of the air in our interferometer. So we put the interferometer, we don't put the laser, but we put everything pretty much beyond the laser into a giant vacuum system. And then there are technical noises, and these are types of noises that actually come from electronics, or maybe the laser itself, or some aspect of the detector components that just we didn't design it right, or we don't have enough control over some aspect of it. The best example of that are wavelength fluctuations and amplitude fluctuations of the laser. All right, so here's a very, it's a somewhat complicated picture, maybe not for this audience, but it basically shows our predicted sensitivity. And the thing that we're doing here is we're using our understanding of all the physical processes that produce the noise to basically come up with a series of curves on this graph that model the interferometer. And the thing, there are a couple things to notice here. The first is that that quantity strain on the y-axis, the vertical axis, it's 10 to the minus 23, which is a little bit more than I said before, but that's because we are actually measuring it as a function of bandwidth. So it's basically per square root of hertz. The second thing to note, down is better. So obviously we want to make the interferometer as quiet as possible. We want to reduce the noise as much as possible. So anything we can do to make those curves go down on the graph, we will try and do it. And the last thing to point out, I guess, is that the x-axis, the horizontal axis, the frequency goes from 10 hertz to a little bit more than 1 kilohertz. And if you recall, if you took a physics class where they talked about acoustics, this happens to be the band in which human beings can hear. So these detectors are actually, we call them audio band detectors. All right, let me keep going through there. So now let me tell you all the components that we put into the detector to basically reduce the noises and produce the curve that I just showed you. And as Colin pointed out, we use Fabry-Perot cavity. So that picture on the left is an interferometer. You probably recognize the laser, the beam splitter, the mirrors. We call the mirrors test masses. So you'll see them labeled as N test masses. But you see there's a lot of other stuff in there too. There are input test masses, mirrors. There are Fabry-Perot cavities. There are things called recycling mirrors, power and signal recycling mirrors. And each of these enhancements to the interferometer basically make it more sensitive. And I can go into more detail if people are interested, but basically what I want to walk you through now is you know, what do these things actually look like and what do they actually do? So first we start with a laser. Our laser it's actually not quite 200 watts anymore. It's we've descoped the laser to about 100 watts. Maybe we'll get to 150 at some point. All right, but it produces very pure light. We stabilize the laser, which means the wavelengths are very well controlled. The amplitude, the power fluctuations are very well controlled. The laser operates in the near infrared at 1064 nanometers, so just a little bit in the infrared region, just outside the visible region of the spectrum. Very important to note that working with this laser requires you to be ultra clean because dust at this laser is very susceptible to damage. And if dust gets on the mirrors or something like that, the laser actually blows up or the mirror blows up. So we work, yeah.
Just on the laser subject, if I'm not mistaken, including a Fabry-Perot and the 4 kilometers, the total distance travel is about 1,200 kilometers, right?
I think that's right. So it's
okay.
I'll do. So the Fabry-Perot has a finesse of I think it's round trip 280. So multiply 280. But there's another. So that gives you roughly your 1,200. But there's another factor there, and that's the power recycling mirror. So this whole system is a very complex optical cavity, and there are multiple cavities in it, and they're all coupled together. That power recycling mirror actually adds another amplification factor of about somewhere between 50 and 60. So the light that goes into the Fabry-Perot cavity rattles around over 4 kilometers, back and forth 8 kilometers, about 300 times, 280 times. But then it gets back into that center where the beam splitter and the input test masses are. It goes back towards the power recycling cavity, and as its name suggests, that sends the light back in to the interferometer, and it does that about 50 times. So there's an extra factor of 50 that you've got to worry about.
All right. How do you basic optical physics is you need coherence length equal or longer to the arm length to get visible fringes. So at 1,000 kilometers, how do you get a laser with that long a coherence length?
Yeah, so the laser follows the Fabry per arm cavity. So we do this in sort of a stepped fashion. The laser itself, all right, there's a reference cavity that's a very stable cavity that a little bit of the laser beam is picked off. It goes into the reference cavity, and basically we read out changes of the laser wavelength or frequency in this case to the reference cavity using something called the Pound-Reaver Hall locking scheme. All right, and that gets us about a stabilization factor of 10 to the minus 2 or 10 to the minus 3 hertz per root hertz, depending on the frequency you're looking at. Then we have another longer cavity called a mode cleaner cavity, which is about, I think it's 16 kilometers long, all right, which provides additional stability. And we use the fact that we can make our cavities very quiet. In other words, because they're suspended, that's what those little wires are that are shown touching the mirrors. The ground motion, anything that's trying to move them is suppressed, and I'll show you a picture of that in a minute. Ultimately, it's the Fabry per arm cavities themselves that actually have the best stability. And if you write down the math, you get that the stability that you can achieve is basically the delta frequency over frequency is equal to minus the delta length over length. And because our lengths we're stabilizing to 10 to the minus 18 meters, the frequency stabilization is quite good. So in fact, the laser itself isn't super, well, it is very coherent. I shouldn't say that it isn't super, but what it's doing is there's feedback from all of these hierarchical length control schemes that feed back to the laser and change the frequency so that it follows the cavity itself. So in an absolute sense, we're not that stable. I mean, we are stable, but not compared to atomic clocks, maybe, for example. But we're stable relative to the interferometer. In fact, in that sense, we're the most stable laser ever built. Does that make sense?
It does. Yes, it does.
Okay. So I talked about the laser. One of the things that maybe doesn't get talked about a lot in gravitational wave detectors, but really is the heart of it, is the seismic isolation system. So we talked a little bit about going underground with CAGRA. Since we're not underground, we have to actually build these massive aluminum objects. We call them inertial seismic isolators that actually have sensors in them. In this case, the sensors are geophones and seismometers that measure the motion on the ground, all right, sense the motion on the ground, and then feed back. So we use a lot of feedback control that basically suppress the ground motion by about a factor of 1,000 or a few thousand, again, depending on what frequency that you're operating at. And again, because we worry about contamination, you have to do this very cleanly. So these are exquisitely well-engineered systems, and we have basically every mirror that you see in the interferometer, every suspension of mirrors that you see in the interferometer has one of these. There are different flavors on them, but it has one of these there. The last thing we do to isolate our mirrors is we put them in suspensions. And again, I'm not sure the audience, but anybody in the audience who's taken physics and mechanics will remember something called the harmonic oscillator. And a suspension, a pendulum, is in fact a harmonic oscillator that if you are at the suspension point, so if I have here's my suspension point, here's my object that's suspending. If I move it very slowly, I don't have it. Well, no, I don't. Well, maybe I can do this in real time. Hold on. All right. I've never done this on Zoom before. I've only done it in real life. Okay, so if you move, the suspension point is my finger, the object that we want to isolate is, in my case, AirPods. This would be the test mass and the interferometer. If I move very slowly, all right, you can see that the motion of the mirror, the white object, the mass, follows my motion. If I move it very fast, you can see that, well, yeah, it jiggles around a lot, but it doesn't really move relative to my motion. But if I move it just at the right frequency, I'm not moving the suspension point, my fingers very much, but I'm really moving the mass quite a bit. And that basically what I've just demonstrated for you is something called a transfer function. All right, at low frequencies, the suspensions don't actually do anything. That's where the seismic isolation system comes in that I showed you earlier. At the resonant frequencies, you actually get amplified motion, but we suppress that because we have basically ways of measuring the motion of the mirrors and correcting for it. And then at high frequencies, the motion is greatly suppressed. It goes as sort of 1/f² there. So these again are very well engineered systems, and I should point out that there are actually 4 of them. So we have 4 stages. I'm only showing you the last 2 stages here. And the mirror, the ultimate mirror, I don't know if you can see my mouse, but the mirror at the bottom here, all right, is held up by 4 glass fibers, all right, and that's it. So each of those glass fibers supports 10 kilograms. So the only physical contact that the mirror has with the outside world is through those 4 glass fibers. And that turns out to be a very, very effective way of doing isolation. Here are the mirrors themselves. They, as I have talked about, they're really, really very, very precisely manufactured mirrors. What you see is reflections of light off the front surface of the mirror, the reflected mirror. And then the last thing I'll talk about, which again doesn't get a lot of press, I would say, when we give presentations, but I think is really important because it's really another major engineering feat, is that because we have to control basically the environment, we don't want the atmosphere to interact with the laser light. We put in a vacuum system. And this vacuum system, you can see it under construction here. This is in Louisiana. It's big. It's about almost 10,000 cubic meters of volume. And it's ultra high vacuum. So it's between 10 to the -8 or 10 to the -9 torr, which is about, 100 billion, maybe 10 billion. The pressure is 1/10 billionth of what you have in atmosphere. And so this is one of the largest high vacuum systems in the world, and we have them at each observatory, and actually maintaining these vacuum systems is a real challenge. And by the way, we are always looking in LIGO for good engineers, good scientists, but particularly good vacuum engineers. So I encourage you, if you're interested, to contact. Yeah.
Dave, with respect to the picture before, why have you guys in this state site have remained above ground and not gone under like Japan?
Expense, money.
Okay.
Well, again, it comes back to, if you understand, so you start with the science requirements. You say, okay, if I want to detect black holes of a certain mass and a certain distance away, or neutron stars, which we'll talk about in a minute, I need a certain sensitivity. What do I need to achieve that sensitivity? And the answer is you need 4-kilometer arms. In some sense, well, okay, I'll come back to that. All right, you need certain laser power, you need certain kinds of mirrors. The mirrors have to be good, the control systems all have to be good. You have to understand the seismic environment. And it turns out for LIGO, when the first detector, we're operating our second detector now. We've actually done this twice. When the first detector was built, the requirement was that you could work on the ground, but you had to have these sophisticated seismic isolation systems. And if you want to go underground, you can do that, but that comes at a cost, because then you have to dig out you have to dig a tunnel down below, which means you have to look for sites that you can do that sort of thing.
So essentially, if you can already measure 10⁻21, why go under?
Correct. That's
Okay.
that's effectively correct. I will show you at the end of the presentation that there's new observatories being built that are also going to go underground. At some level, it's just a sort of a choice between, do I think I can get the funding to build, something this big, and do I absolutely need it to be able to do the science that I want to do?
Okay.
It really does come down to that.
Okay.
So okay.
Thanks.
All right. So now I'm going to talk about astrophysics. So I gave you some questions at the beginning of the presentation that we can ask, and now I'm going to sort of start to try and answer those questions. And these discoveries were made over the last 7 years by this large team of really, really great scientists in the LIGO scientific collaboration and the Virgo collaboration. So the discovery, if you will, that put us on the map, the video at the beginning sort of highlighted this, was the first detection of a binary black hole merger. So as the name implies, these are two objects, compact black holes, that are bound together orbitally. And as they're bound together, they're orbiting around one another and they're radiating gravitational waves. The graphs that I show you on the left are, well, the upper graph is what was recorded on a detector at Hanford. The lower graph, all right, the blue, is basically overlaying the Livingston detector plot, and you might see that there's something shifted and inverted. If people care about that, I can explain that. But basically, you can see that these two signals are very, very consistent with another. They're not perfectly consistent, but the frequency behavior, the wave at further back starts at low frequency, and then the frequency gets a little bit faster and continues to go faster and faster, get shorter and shorter. The frequency gets higher and higher. The wavelength gets shorter and shorter. The amplitude grows, and then all of a sudden, it all just cuts off. And that's very characteristic of a gravitational wave that's been produced by the collision of two black holes. And in fact, the information that you can extract from those waveforms tells you a lot about what the masses of the black hole were, what the mass of the final black hole is, what the where the black hole might come from, and even although it's very, very difficult, you can get the spins of the basically the rate of that the event horizon, if you will, is spinning there. And so now I'm going to come back and answer a question that I posed earlier about why do we have multiple detectors, and this really, if we saw a gravitational wave signal that didn't look the same in both detectors, taking into account the difference where they are on the planet, you wouldn't believe it's a gravitational wave. So we do a lot of statistical analysis, but we have to have what we call coincident detection. There's another reason for it, which I'll come to when I talk about the neutron star. So now I'm going to show you a beautiful simulation that was done. Once we were able to measure these waves and extract the information about the waves, you can actually then take the information and use theory. So this actually uses Einstein's general relativity equations, the Einstein field equations, and then turns them into visualization. And this was done by Kip Thorne's group, and also a group in Cornell led by Saul Tucholsky. And what you're going to look at here is basically the last 20th, maybe, or 0.2 of a second of the lives of these two black holes that are trapped in each other's sort of death spiral, if you will. One of them turns out to be about 36 times the mass of the sun. The other is about 30 times the mass of the sun. And so let me run the video here. So you can see they're orbiting around. And by the way, what you see behind them is space, the dynamic space-time. So the starlight is bending because the geometry is changing. And you can see they come together, they collide. And what's left behind is basically a bigger black hole. It's about 62 times the mass of the sun. And in this case, there was a huge amount of mass energy conversion. So at the last instant of the merger, right when the black hole formed, and the two black holes formed into a bigger black hole. Basically, 3 times the mass of the sun was radiated in gravitational waves. So that's an immense amount of energy. This at the time that it was observed in the Earth, it was the quote brightest object that in the universe, in the term that in gravitational waves. All right. So now you can look at these with frequencies, and I don't know if you can hear the sound there, but basically, can you hear the sound or not?
Yes, it's
okay.
Good.
Great. So that thump that you hear is in fact basically the signal that was recorded on our interferometer, and now the data is being plotted as what's known as a spectrogram, which to me is pretty amazing, that these two black holes, which are 30 times the mass of the sun, they're about 1.2, 1.3 billion light years away, which means it took that long for the signal to get to us. At the end of the day, when they hit the detector, they're recorded as this little thump. Yeah, so this big massive object turns into a little thump in our detector, but it carries a lot of information. So this was a big deal. Ray Weiss, Barry Barish, and Kip Thorne won the 2017 Nobel Prize in Physics for this discovery again. And they would point this out too, that they were part of a team that made that discovery. I was fortunate enough to actually attend the ceremony, and that picture in the upper right-hand corner is a picture of the dessert that was served at the Nobel ceremony. And I'm not sure if it's black holes or it's some interesting astrophysical thing. I don't know what it is, but it was very, very good to eat. So, all right. In the last couple slides, I have 2 more topics to talk about. The first is something called multi-messenger astronomy. So the black holes that made LIGO and LIGO so famous have a certain characteristic. They're black. In other words, we don't expect to be able to detect them any other way except through their gravitational radiation. And in fact, that may not be completely true. If these black holes happen to be in a gaseous environment where there's basically matter, and the black holes are matter is accreting on the black holes and they merge, you could actually see a signature in the electromagnetic band. In other words, you could measure it using telescopes. But we haven't, and none of the black holes that we've seen so far have been accompanied by any optical or what we call electromagnetics signal. The neutron stars are different. The neutron stars are, as I said, they have matter in them. They have 1.4-ish solar masses of mostly neutrons, packed together at supernuclear densities. So the density of these objects is immense. In other words, what I've been told is if you take a teaspoon of neutron star matter, because it's all nuclei, if you weighed it on Earth, it would weigh 1 billion tons. Just 1 teaspoon of it. So that gives you an idea of the density of these things. Consequently, when they come together and collide, they do so in a spectacular fashion. So they not only produce gravitational waves, which they're producing before they collide, up to the point they collide, they're also going to radiate in all of the bands of the electromagnetic spectrum: visible and infrared light, X-rays, radio waves, cosmic rays, millimeter wave. They also, we believe, will produce energetic neutrinos that you could detect. So this kind of event where you have objects that are moving relativistically that have matter in them, and this would be true perhaps for a neutron star colliding, merging into a black hole also, under certain conditions. You're going to see you're going to be able to look at this, if you will, probe it, observe it, using a lot of different modalities in your toolkit, using optical telescopes and radio telescopes and cosmic ray detectors and X-ray satellites and gamma ray satellites. So this kind of event is called is known to people in the business as multi-messenger astronomy. The messengers in this case would be the gravitational waves or the photons or the neutrinos. Everybody knew about this before we detected a binary neutron star, but it just so happened that the first binary neutron star that LIGO and also our partner Virgo in Italy detected actually came with a lot of happy surprises because of these other messengers, and I'll tell you a little bit about them. So the second reason why we have multiple detectors is because one detector is really not very good at telling you where the signal came from on the sky. The analogy that a lot of people in gravitational wave physics use is that a signal gravitational wave detector, an interferometer, is really a microphone. It picks up signals from almost any direction. If the signals are further away, they're weaker. There are certain places where, depending on the orientation of the interferometer arms, they could be weaker, they could be stronger, but in general, it's not very good. So how do you break that degeneracy? How do you get information that would allow you to localize the event? And the answer is you use more detectors. In principle, you need 3 to be able to triangulate a source. So the idea is that an object, neutron stars collide, and they're picked up by each of these detectors, in this case, the 2 LIGO detectors and the Virgo detector, but there's a time difference between them. And we measure waves very accurately. So we know how to measure the time difference between when each of the detectors receive the signal very accurately. And that tells us, that gives us good, not great. In fact, relative to people who work with telescopes, it's pretty poor, but it gives us enough information that we can tell our friends who operate telescopes and satellites that they might want to be looking in a certain direction. And so basically we're doing triangulation here. In this case, it's with these 3 detectors. It turns out more detectors is actually even better still. All right, so in this case, the 3 detectors that were operating at the time, and this was in August of 2017, were the 2 LIGO, Hanford, and the Virgo detector had just come online. So there's, like many things in life and in science, there's an element of luck that happens here, and we were quite lucky. So what did we see? So we were able first to see a gravitational wave. All right. And that spectrogram, the plot on the bottom, is the data plotted as time and frequency. But independently, and actually even before we knew we had a gravitational wave, the satellites, in this case, it was the Fermi satellite operated by NASA and the Integral satellite operated by ESO, look for bursts of gamma rays. And they happen to independently see a gamma ray burst about 2 seconds after the end of our gravitational wave signal. And this was a remarkable coincidence because you were able to see both of these things at the same time, or nearly the same time. And in fact, it was recognized really by the Fermi team, maybe a little bit before the LIGO Virgo team, that this event was really, really spectacularly special. So the simulation I'm going to show, and since you can hear the sound, I'm going to try and synchronize this. This is a wonderful simulation from NASA showing basically 2 neutron stars that are orbiting around one another and colliding, much like the black holes I showed you before. But I want you to watch what happens as they get closer and at the end when they collide. So let me see if I can get this going. So they're orbiting around one another. That trail of white is basically nuclear matter being off, and then all of a sudden they come together. And you may have heard it, this little whoop, right? And then you see this dramatic emission along basically the perpendicular to the orbital plane of first gamma rays, then lots of nuclear matter, which are moving out at relativistic speeds that are like, in some cases, 10% the speed of light, in some cases more than that, all right? And this was a remarkable event because we were able to catch it independently with gravitational waves and with gamma rays. And that allowed us to do something really, really important coming back to this localization. So if you look at the data independently, if you ask how good could LIGO have done without Virgo localizing this event, what I'm showing here is basically a map of the sky. Picture yourself in the center and you're sort of looking out of the screen. And those colored regions are the regions where the event might have come from. And so you see the LIGO banana, I call them bananas, they're called air ellipses and by the astronomers, are quite large. You can see the gamma ray localization from the Fermi and Fermi integral satellites are really, really large over large fractions of the sky. So there'd be no hope that you could, or very little hope with the instruments that we had at the time, that you could actually look in the sky and nail down where this event came from. Of course, it came from a very localized source. The objects are very small and very far away. But when you add the Virgo data, you get something that's more reasonable. That sort of light green error box there is about 30 square degrees in the sky, which is large by astronomical standards, but small enough so that a good and motivated team of astronomers can go and hunt for where that came from, and that's what they did. And so this is a great simulation. We're going to zoom in on that 30 degrees, and what those dots are galaxies that are all roughly a few hundred, maybe 100 million, few hundred million light years from us. And we zoom in on one. This is galaxy NGC 4993. It's about 130 million light years away. And 11 hours after we saw our signal, and after a very concerted effort by a huge number of astronomers, somebody told me that 70% of the world's telescopes actually looked for this particular event. They saw this little object, all right, which I'll highlight, and I'll show you. Actually, there's a better picture of it here. This is what we call GW 170817, what the astronomers call SSS 17A, what the gamma ray physicists call GRB 170817. I think this was A, I don't remember. And they were able to catch this guy in the act. So that arrow is pointing to two different two different views of this galaxy with that object that gets fainter over time. And that object is called a kilonova. It is basically the remnant of those two neutron stars that collided together. And a very interesting series of questions, which we don't have definitive answers to, is what's left behind. Is it a neutron, another neutron star? Is it a black hole? Probably it's a black hole, but nobody really knows that. And so that's one of the still outstanding physics questions. But perhaps the best discovery that came out of this was really done by the time domain astronomers and nuclear physicists who study kilonova. And the fact that that color is changing and the object is fading, well, that was caught over time. And this is a time view of the spectrum in micrometers of the signal as a function of time. So what you see is that the signal is decaying away. So it's getting dimmer and dimmer and dimmer. But you also see there are those time stamps that show these bumps in the spectrum. And those bumps in the spectrum are actually clues to what's happening around the kilonova as a function of time. And remember, I said that these are giant nuclei. They have lots of neutrons. Those neutrons, when they collide, a lot of them get dispersed, but it's so dense. There's such a rich environment of neutrons there that those neutrons can aggregate to form heavy nuclei. They can collapse together to form heavy nuclei before a process known as inverse beta decay takes place that would convert them to protons. So there's a lot of theoretical work that's gone into this over the past really 30 years. But the prediction of theorists is that those bumps actually are signatures of the formation of the heaviest elements in the universe. And so you can ask yourself, where do elements come from? Well, we've known for a while that the lightest element, hydrogen and a bit of helium, came directly from the Big Bang itself, at the origins of the universe. Some of the mid-mass elements, those ones in blue there, come from either exploding white dwarfs or supernova. And these are just nuclear processes that are taking place in the star that lead to basically the formation of heavier and heavier elements as the star burns its nuclear fuel, and then it explodes. But to get to the really heavy elements, the ones that are shown in yellow, all right, you have to basically have a process that you can't find in exploding massive stars. It's called R-process nucleosynthesis, or rapid nucleosynthesis. And the theory basically had predicted for a long time that you might find this in the collision of these two neutron stars. And in fact, that's exactly what happened. That the data from all the observational astronomers was able to be compared against the theory and showed that you could form elements like gold or platinum or iridium or uranium, for that matter. So this is really confirmation that the heaviest elements in the universe are predominantly, if not completely, formed by the collisions of these two neutron stars and the subsequent formation of a kilonova. So that's a really remarkable piece of science that got done with this event. So since we've been operating, we've actually had 3 observing runs since 2015. We've detected a total of 90 gravitational wave events. The vast majority of those events are black holes, and you can see all the black holes that we've discovered. That includes basically the every event is 2 black holes coalescing into a third black hole. This just is a nice way to visualize them. We've also seen some neutron stars. We've seen a couple of neutron star collisions. We've seen neutron stars colliding with black holes. So we're starting to get a real handle on how many kinds of these events there are. What is the nature of the masses of black holes? Are there a lot of heavy black holes? Are there a lot of light black holes? And these are questions that astrophysicists are really quite interested in. So the last few minutes, I'm just going to talk about what I call new detectors and new horizons. And the highlights of the events that I've shown you so far in the last couple of slides, really, it turns out, are relatively local to us in our universe. So there's a nice picture, again, I credit NASA for this, showing basically the evolution of the universe. The cone that you see is basically a conic representation of the universe, starting with the Big Bang, quantum fluctuations, a rapid expansion of space and time, inflation, the formation of basically the cosmic microwave background. That's that mottled green and blue and yellow and red there. Then so-called the dark ages, where no light could escape. Then about 400,000 years after that, or 400 million years after that, the first stars form. It took that long for all the matter from the Big Bang to aggregate into clumps to form stars. And then the universe expands, and we get to where we are today on the right. Turns out, And the way you can look at that actually in star formation language is that picture on the left, which is a radial picture. As you start at the center, that's where we are, that's Earth. If you go out, that gets you out to higher redshifts, which in the language of distance gets you further back into the universe. So a redshift of 100 is looking, a couple of 100 million light years, a couple of 100 million years after the birth of the universe. So those dots that you see are basically mergers of neutron stars in yellow, mergers of black holes in gray there. And the two events that I just talked about are you can see they're pretty close to us in terms of distance. They're redshifts that are less than 1. In the case of the binary neutron star, much, much less than 1. So the detectors that we've built, even though they're very sensitive, they don't see out that far. They can only see back, at best, maybe a few billion light years. And that's for the most massive black hole sources. So we're missing a lot of what's happening in the universe because our detectors aren't sensitive enough to see further into the universe. So that's why we want to build new detectors. The idea, and I want to come back to where I started this, is that the fact that you can build interferometers and the fact that you can make those arm lengths long, there's nothing fundamental about a 4-kilometer arm length interferometer. Why not make it 10 times larger? Well, the reason you might not have done that to begin with is it costs a lot of money. It certainly costs a lot more money. So you wouldn't invest that up front. But now that you know that you can detect gravitational waves, it shouldn't, building a 40-kilometer interferometer is not out of the question. And so that's what we're doing here in the US. In Europe, they're building a magnificently complex interferometer called Einstein telescope. It's underground, much like Cagra's underground. And in Europe, to build something that big, you really do have to go underground. There's no good place to put it. But it also actually gets rid of some of the seismic noises I've talked about. And these two what we call next generation or third generation observatories will literally be able to see out to the beginning of the star forming universe. So if there were stars at the beginning, once they formed into binary systems and they evolved into black holes and they collided, these detectors will be able to see that. So we'll be able to see basically the entire universe with these next generations, which allows us to look very, very far back in time. Finally, I've only talked about what we call the millisecond period gravitational waves. These are the gravitational waves that you can detect with these kilometer scale detectors on the ground. Like electromagnetic waves, gravitational waves come in a spectrum. So at the shortest wavelength or the highest frequency, we have the ground-based gravitational wave detectors looking at compact object mergers, black holes and neutron stars. But you can build detectors that go out in space. And that picture that I show you is actually a concept of a detector that will be built and launched by the European Space Agency and NASA, called the Laser Interferometer Space Antenna, which will look at much longer gravitational waves that have frequencies of microhertz to millihertz, which correspond to periods of minutes to hours. The nice thing about space is you can build long interferometers. So these arms are 2.5 million kilometers. You can even go further. And you can look for gravitational wave sources from supermassive black holes, like the one I showed you at the beginning, that collide. We know that galaxies collide, and they produce gravitational wave signals. Our friends who operate radio telescopes actually have a very clever way of doing that, called pulsar timing. And they're actually, I think, very, very close to releasing some very interesting data. And then finally, the longest gravitational waves in the universe are actually at the scale of the universe themselves. They were produced at that moment of the Big Bang when the quantum fluctuations were dominating. They were embedded in space-time, so when space expanded, the wavelengths expanded and greatly redshifted. And so these wavelengths are measured on scales of fractions of the universe. And there, the detection technique is slightly different. You can't directly look at those waves, at least we don't think so. So you have to actually look at how they imprinted on the cosmic microwave background. These kinds of detectors that look at gravitational waves are really going to be doing forefront astronomy in the next, really in this century and maybe even beyond. So I think I'll stop there. Thanks for your attention. I hope it was interesting. And there's links for more information. And I'm happy to take any questions.
Yes, thanks, Dave, for a very wonderful and enlightening, gravitationally speaking, presentation. There are a few things I would like to ask beforehand. You mentioned that these things, the waves, the gravitational waves, travel generally unimpeded through space, and
Correct.
they're produced by huge violent collisions. But why are they detected in such minuscule length scales?
Yeah, so it has to do with the concept of strain.
Okay, so does that mean space-time itself is sort of dampening the
it's not so much dampening. It's space-time is stiff. So in other words, it takes a huge amount of mass and accelerating massive black holes to produce tiny compressions in space-time itself. So the analogy that I would give the
analogy is similar to what we experience in normal material stuff with man-made strains and piezoelectric stuff and all that.
Exactly. But the stiffness, you can do a back of the envelope calculation and you find out that, if you make some, if you don't worry too much about the units, that the stiffness of space-time is about 10 to the 20th more stiff than diamond. Okay. So that gives you, that's why these massive, objects moving at relativistic speed producing. To answer your question, you said damping, and I think that's an important concept. That if there were something that would absorb gravitational waves or disperse them or damp them, that would show up actually in the speed of the gravitational waves. We actually look for that. We actually try and measure whether or not there's dispersion in the gravitational wave signal, whether there, we can measure, I didn't talk about it, but we can actually measure the mass of the graviton, if you will. Idea, it should be zero. Our data is consistent with zero, so we say that it's zero.
Okay, and the one in one of the graphs you showed the Livingston and was this and your place, the interferometers are slightly this way 90-degree off. Is that why the graphs were shifted?
Yep. Well, it's why. So the graphs were shifted to take into account the time difference between the arrival of the signals. So it just so happens that the gravitational wave was traveling such that it actually came through the Earth, hit the Livingston detector about 6.8 milliseconds earlier than it hit and that's just the time delay of the time difference of travel. The inversion comes about exactly from what you said, that the L in the Hanford detector is different from the L in the Livingston detector. So there's a 180-degree phase shift on the signal between the two detectors.
Okay, and I think there's a concept that was mooted by Archibald Wheeler, and later on, I think brought on by, made famous by Hawking. I think it's called Hawking radiation. Would that be gravitational, and would that be detectable, or do we have to go to a very large array into space kind of thing?
So the answer is, in principle, it might be detectable. In practice, it seems very, very difficult because the Hawking radiation is, produces, either electron hole pairs or particles at the surface of the event horizon. The amount of conversion of basically Hawking radiation in this, infrared radiation or electron hole seems to me to be very, very tiny. So I'm not aware of anybody that's actually seriously proposing to look for them, but that doesn't mean that it shouldn't be thought about.
Okay. I've known LIGO since I was in undergraduate time. So why has it taken LIGO so long to produce credible results? I understand the concept of building rockets. It takes a long time to perfect the thing and all that. Is it similar to that, or there are other constraints?
I was looking for a slide, but I don't have it. I would say that the answer to that question has a couple of components to it. The first component to it is when the interferometers were first proposed. All right, people still questioned whether gravitational waves were interesting. All right, so it took a long time from the time that you could write down a concept, this concept that Ray Weiss put down, till the time that NSF funded it. That took 20 years. All right. So, but if you say from the start of the proposal to fund to fund the observatories really got green lighted in the early 90s. It took 10 years to build the observatories. It took to design the detector, and it took a few more years to build the detector. And I think the reason for that is no one had ever built anything like this before. It's really a completely new concept. The engineering that needed to be done was quite different from the engineering that needs to be done for a lot of other types of instruments, or it's a lot more precise. Like I say, the first time you hear that you're trying to measure displacements, that are, subnuclear, you think to yourself, how can I do that on the Earth? So I think a lot of it was just doing that. It turned out that it was a lot more complicated to actually understand how the detectors work and make them work sensitively than anybody ever envisioned. So the first generation of LIGO detectors were built between 2000 and 2001, maybe 2002. And when you build them, these are, again, there's a lot of parts to them, a lot of components, they all interact with one another. You had to figure out, first of all, how to just get the interferometer to operate stably. So how do you lock the interferometer? How do you get the Fabry-Perot cavities to be stable? How do you get, the mirrors tend to want to bend, because they're suspended. The laser beam can actually force the mirrors out of alignment just because of radiation pressure. So there were tremendous amount of things that had to be understood to make them work stably. And in fact, once they were built, it took, I think, 4 years from the time that the first generation was built in 2002 till the time they were actually operating at their first sensitivity, which in this case was it was 10 times less than where LIGO was operating at. And that took a long time, longer than anybody expected. So, and then we went through this again because we knew that, well, we didn't know. The fact that the U.S. National Science Foundation funded LIGO, they were making two bets. The first bet they were making was that gravitational wave sources existed and that they would be interesting to detect and they would tell us something about the universe. The second bet they were making was that you could actually build a detector that was sensitive enough to see these gravitational waves. And in fact, that bet was a little bit hedged in the sense that when NSF funded the building of the LIGO observatories, it funded not only the building of the first generation of detectors, which may not have detected or may detected. A lot was not known about the rates of gravitational wave events, but it also committed to building an upgrade, the one that we operate now, that if the first generation detector worked, in other words, it met its design goals, even if it didn't see anything, NSF would commit to building a second generation detector. So that process took a little bit of time. So I think what you're seeing is the accumulation of basically multi-generational detectors, a lot of trying to understand how the detectors work. And I point out that we show these data, and it really sounds wonderful, but we don't completely understand how our detectors work. There's still things we just don't fundamentally understand, particularly at low frequency. Our low frequency sensitivity is not where it should be, and we don't know why. And we've been studying it for 20 years.
On that note, I'd like to know, my introduction to gravitational waves was on some Practical Wireless magazine, where they showed the picture of Prof. Weber hanging together with his aluminum cylinder. I would like to know, why did Ray Weiss go completely the other way around to optics and not just follow the idea of Weber or build upon Weber's idea and go larger on Weber's style?
So the story that Ray tells is that, well, first of all, even Weber built this detector. It was actually a very sensitive detector at the time, but Weber was claiming to see signals that clearly were not, that he was calling gravitational wave signals that were clearly not. If you just did the energetics, the signals that he were seeing would have to be produced from the sun exploding. All right, so Weber got himself into a lot of trouble by basically insisting that he was seeing gravitational wave signals when clearly the community knew he wasn't. So that was the first piece of the puzzle. That got Ray thinking, well, maybe there is something to this, but obviously this isn't the way to do it. And the story he tells, and I can't verify, but the story he tells is that he was actually teaching a class in general relativity at MIT, and he's an experimentalist, and so he had to learn general relativity right before the student before taught it, and he came to the chapter on gravitational waves, and he started asking himself, I really wonder if there's any other way to do this. And so he basically came up with a problem in his head. Could I use an interferometer to detect gravitational waves? And it turns out this idea had been around before. There was as I said, there were two Russians, Pustovoit and Gershenstein, who had proposed, but not done a very serious study of interferometers. They just said interferometers would be a good way to do it. Ray actually, gave an exercise to his class. So the first gravitational wave designers were graduate students in relativity, and then went through and wrote this really phenomenal paper that never got published. He didn't publish it on everything you need to do to build a gravitational wave detector. In fact, it was quite interesting. You may be familiar with a book that goes by the name of its authors, Misner, Thorne, and Wheeler. I don't know if that book is familiar. It's a big book, that is everything about general relativity, and it's one of the authors is Kip Thorne. There's a problem in that book that actually says you can prove that lasers will never be useful for detecting gravitational waves. And so Ray actually convinced Kip that was not true.
Okay. All right. Any questions from the floor? Nothing yet? No one raising hands? Nothing yet. Then okay, then another thing, I imagine gravitational waves, totally a novice point of view. Something like shock waves or acoustic waves or matter waves in matter where polarization is messed up. That's acoustic waves on simple devices. They don't travel in simple what do you call horizontal or vertical polarization, but they get messed up into material and all that. I presume gravitational waves behave in a similar way. So how do you? So how does does it help that to have the 90-degree arm on the LIGO, or does it really? Is it able to? One is, are gravitational waves messed up in polarization in such a way, and two, can the 90-degree arm really help in detecting these?
Yeah, so the answer to the first question is, so let's come back here. So this is one polarization of a gravitational wave in a certain calculational basis, the transverse traceless gauge. If you were to rotate this by 45 degrees, so that instead of having a cross, you have an X, that's the other polarization. Those are the two fundamental polarizations that are predicted by general relativity.
Okay.
The polarizations are not scrambled, again, because gravitational waves don't interact with it, but the production of the gravitational wave polarization is certainly depends upon the source, right? So if you think, I'm going to stop that because it makes me dizzy. If you think about two black holes orbiting around one another like this, and so this is the plane of the orbit, so they're going like this. All right. It's not hard to imagine, since they're accelerating and they're orbiting around other, moving relativistically, that they're producing circular gravitational waves. So they're you basically an admixture of those two polarizations. If I look edge on at the orbit, so I turn the orbit this way or this way, it looks like they're doing this, right? And that's producing linear polarization. And it turns out that the gravitational, they're much more effective radiators and things, but the polarizations don't scramble per se, because again, they just don't interact. The sources generate the gravitational waves, but their non-interaction with everything else means the polarizations aren't scrambled. There's one, it's not about polarization. Gravitational waves follow geodesics, follow straight lines in geometry, so they are lensed. So you could actually see lensed gravitational waves, just like you see galaxy lensing, things like that. So the other thing to say is that there are different theories of gravity. General relativity, of course, is the one that everybody knows because it's successful and it's been proven true again and again and again. But there are more complex theories of gravity, a class called Chern-Simons, that actually predict more polarizations and different kinds of polarizations. And again, that's something you can search for. Turns out in the collision of the binary neutron star, the black hole, as the event horizon relaxes, it rings down to its final state after the merger. There's information about higher order modes and polarizations that you can look at there. And of course, again, we've looked for that, and there's no evidence that general relativity is wrong.
Okay. Since we are dealing with mostly cosmic events, can the gravitational wave detection and its subsequent calculation somehow contribute to knowledge of the Hubble constant?
Yes, and I didn't talk about that. Let me see if I have a slide. No, that's not it. No, I don't. Unfortunately, I don't have a slide. So, yeah, the gravitational waves have a very nice characteristic, and that's if you know what the source is. In other words, you know that you have two black holes, and those black holes are a certain distance away. And that distance is important. We're going to call it the luminosity distance, and they radiate because of their masses and their orbital dynamics. You can calculate exactly what the gravitational wave signal is on Earth. And in fact, that's how we search for gravitational waves. But more importantly, you can calculate the amplitude, because the gravitational wave signal falls off as 1 over r, not 1 over r squared. So if you detect a gravitational wave with LIGO and you can extract the parameters of the source, including the distance that it came from, you have this luminosity distance. You've got it for free. And that's great, because if that object is moving away or is far away from you, of course it's moving, expanding like in the universe around it. Yep. And so if you can identify, it turns out that what Hubble observations tell us is that the velocity of the expansion is proportional to the distance, yes, from the Earth, yes, or from where you're measuring. And if you can measure the redshift, in other words, where physically the object came from, not the luminosity distance itself, because they're different, then you can actually calculate from the data what the Hubble constant is. And so we did that actually. One of the from the binary neutron star, you can measure the redshift because the telescopes find it. And that gives you everything you need. You have the neutron stars, the gravitational wave signal, the redshift, and it turns out that our measurements are not very precise, much less precise than other ways of measuring the Hubble constant, but they actually predict, or the peak, if you will, the most probable value for the Hubble constant happens to be right in between what the other methods, the basically looking at supernova and Planck, tell you. So it's really a remarkable thing that the first time you actually measure gravitational waves, that you get a measurement that's consistent with what you learn from other sources. Now, can we improve that? Can we do better? And the answer is yes. The more of these binary neutron stars that we see, the more we can statistically, we can build up statistics on it. And even with black holes, we can't always know where the black holes are coming from. Like I said, they're dark. They only produce gravitational waves, but you can do statistical inference based on your knowledge of the galaxy. Of the universe, where galaxies are in the universe. And you can use that data collectively. And there's simulations that people have done that show that, when we get to these new detectors, the Cosmic Explorer, the Einstein telescope, the things I talked about at the end of the talk, we'll have measurements that are competitive with, but completely different from the measurements that astronomers use today. And that's actually important, because there is a belief among the cosmology community, the people that measure the Hubble constant, that the measurements are telling them different things depending on how you do the measurement. And so there's a little bit of what's known as a tension in the data, and this could be a way of resolving it. So yeah, it's very interesting from a cosmological perspective.
And how about dark matter, dark energy? Would it be a part of the space-time itself, or would it be something else?
Yeah. So the dark. Let me talk about the dark matter. I don't know enough about dark energy to have to say anything really intelligent about it. But the dark matter.
Dark matter should be a bit more gravitationally interesting.
Exactly, it gravitates, and so where might it come from? After we made our discovery, and in fact, I think even before people were thinking about this, people thought that, well, dark matter could hide in black holes, right? You know, if you have black holes out there, they don't radiate. You can't see them. So maybe there's a distribution of black holes around galaxies. And originally the thinking was they're low mass, what are known as subsolar mass black holes. After our detection, the first detection, there were papers that came out that said, oh, maybe these black holes were actually primordial black holes. In other words, they were formed not by stars exploding, but by basically quantum fluctuations of the universe in the very early femtoseconds, the first instant of the universe, that produced basically massive fluctuations in spacetime that were so severe that black holes actually just formed directly out of these fluctuations themselves. And that turns out probably it's not true, that they're 30 solar masses. We don't know that, but one of the ways that we can get at dark matter, if indeed there are primordial black holes that are dark matter, is if we can look out beyond when stars formed. In other words, back a few 100 million years after the Big Bang. And if we see black hole mergers, it's pretty clear that they didn't come from basically stellar evolution. They came from primordial fluctuations, and that could be black hole. Those could be dark matter. So this would be one candidate for dark matter. There are other candidates. If dark matter gravitates, it should produce gravitational waves. The problem is it has to be relativistically moving, and dark matter tends to come in clumps. So there are also for dark energy, it's a little bit harder to see because we don't really know what it is. But astronomers measure this parameter called W, the dark energy parameter, which is basically a measure of the sort of the tension of dark matter. Of dark energy. What's forcing space to accelerate further and further as from each other point. And we could be measuring that too. So there are a couple ways that we could do that. Like I said, my hope is that we discover something in our data that has no known origin, and after you start thinking about it, that's where you come to discovery. That's how the acceleration of the universe was and dark energy was discovered. So,
Dave, pardon my ignorance on this. LIGO is able to detect ripples in the gravitational space-time behavior, not gravity itself. Am I correct?
We detect fluctuations, dynamic fluctuations in the local gravitational wave field. Those local fluctuations in the gravitational field, not the gravitational wave field. Those local fluctuations in the gravitational field, we go to great effort to make sure that we're only sensitive to those fluctuations that are produced by passing gravitational waves. However, and this is going to be a problem for the next generation of gravitational wave detectors, if an object is moving, all right, by our detector, by one of the mirrors, the gravitational wave field is changing by minute amount because you have a mass that's actually dynamically moving forward. And so it turns out that the source that we really worry about there is the surface of the Earth, the way, you have P waves and S waves that are moving through the Earth that are compression waves. Those actually produce measurable signals, not in our data, but they will in these next generation gravitational wave signals. So you have to come up with clever ways of measuring these fluctuations using a different instrument. And in our case, we would use seismometers or gravity gradiometers, and then subtract out that signal so you can actually get below the noise floor imposed by dynamic gravity gradients. But what we really measure, fundamentally, what we really measure are basically local variations in the gravitational acceleration over those two two arms differentially. That's what a gravitational wave detector does.
Nice, thanks. I think that's about it. What I have from my side. I do not see much questions. 3 messages. Okay, nothing much on the chat either. Just a minute. All right, I suppose that would be the conclusion of our discussion as well as the presentation, Dave. Before we end the night for you, we would like to invite everyone for a photo session. So I hope everyone would switch on their cameras and we will go for a photo session. Yes, Dr. Shima, thank you. And I did see Prof. Riza somewhere. Everybody, please switch on your cameras and we shall take pictures. There's still quite a number without cameras, please. Bit more. Come on, cameras. He's got to go. David got to go and have his supper.
I'm cooking tonight. So.
Cooking tonight. Oops, that's a late dinner. All right, I think we can go. Let's go. Okay, thank you, everybody. Thanks for a good time. Thanks for a good talk, David. Hope you join us in our future other sessions. Have a good day.
All right.
Good night.
Thank you very much.
Thank you very much for your enlightening speech.
Okay.
Okay.
Bye-bye.
Bye-bye.
Enjoy the rest of your day.
Thank you. For the rest of you, the link for attendance, you can scan the QR code presented on the main screen now and register for e-certificate. Dr. Ashima, that will be good for your PhD. All right, that's about it. And we will have the next session, Series 10, somewhere in January. There'll be a local presenter presenting on herbal business and herbs that they have been promoting. I forget what's the company name. Nazri? The company yang Series 10. Series 10. Herb though. Medica Natura, yeah. All right. Medica Natura will be presenting their case on a Series 10 in January. So again, QR code presented. No more. Done? Okay, thank you. Thanks everybody. Have a good day. Salam sejahtera. Selamat berjumpa kembali.